Hello everyone, I'm Paul and today we're solving problem 2048, next greater numerically balanced number. This is medium and the solution for this one is pretty straightforward, so let's start. We are given an integer n and we need to return the smallest number that's strictly greater than n and numerically balanced. And here we have the definition for a numerically balanced number. Every digit d in the number has exactly the occurrences of that digit in the number. So for example, this is numerically balanced. We only have one occurrence of number 1. This is also numerically balanced. We have two occurrences of number 2. And this is also numerically balanced. We have one occurrence of number 1, two occurrences of number 2, 3 occurrences of number 3. Okay, so let's say n is 1. Our job is to find the smallest number that's greater than n, strictly greater than n, and numerically balanced. So if we try 2, for example, here we only have one occurrence of number 2. And given that 1 is different from 2, this is not numerically balanced. The first number that's strictly greater than 1 and numerically balanced is 22. Here we have two occurrences of number 2. And given that 2 is equal to 2, this is numerically balanced. And given that this is the smallest number that's greater than 1, we return 22 with this input. And the solution is simple. We are iterating every number that's strictly greater than n. In this case, n is 1, so we start from 2 and we continue up to infinity. At some point, we will step into a number that's numerically balanced and we return that number. So we start with 2. And the process is the following. Every time we are building a frequency map. In case you know what a frequency map is, here we are storing unique characters. In this case, we are storing digits. Here we only have a 2, so we add 2 with a count of 1. Meaning we only have one occurrence of digit number 2. And given that 2 is different from the amount of 2's in this number, this is not numerically balanced. And we will do the same with number 3, which is also not numerically balanced. And then we do the same with 4, and then with 5, and then with 6, and so on, until we reach number 22. And here we do the same. We build a frequency map with every unique digit as a key. Here we only have 2, and we have two occurrences of number 2. And given that 2 is equal to 2, this is numerically balanced, and at this point we return this. So this is the entire approach. Regarding time complexity, we are trying every number that's greatly greater than 1. So we go from 2 to, given that n can be up to 10 to the power of 6, we can go up to 10 to the power of 7. But we won't iterate 10 to the power of 7 numbers because we will find a numerically balanced number before this. So we can say time complexity will be smaller than big O of 10 to the power of 7. And space complexity is big O of 1. So with this in mind, let's go with the code. Here we are doing exactly the same we did a few seconds ago. We iterate every number in the range from n plus 1 to 10 to the power of 7. And every time we build a map, this is counter from string n. Okay, so we are building a frequency map for each number. And now we have two ways to check the condition. One is we can have a boolean. Next is false. And now for every key and value in map.items, if key is different from value in string format because it's an integer, now next is true, and we break this loop, And here we can say if next, we just continue, else we return n. Okay, so if we try every key and value in the map and they are all equal, we end this loop. In this case, next stays at false, so we return the corresponding number. Now this should work, but we have another way to do this, which is to say if all k is equal to string value for key value in map.items. In this case, we return n. So this and this is exactly the same. Now let's submit this and see if it works. As you can see, this works and it's efficient. And now let me comment this and uncomment this just to show you this also works. Let's submit this. As you can see, this also works, and maybe you are wondering how can we make this more efficient? And the answer is, once we know how to solve this, we can build a lookup table. How can we do this? Well, we can build an array. We'll call this all. This is an empty array. And here we can go from 1 to 10 to the power of 6 to avoid time limit exceeded. And we are trying to get every valid number in this range. So we do exactly the same, and here instead of returning n, we say array.append n, and finally we can print the array. Sorry, this is all, and here this is all, and now we can run this. And now here we have every numerically balanced number, so we can just copy this thing and we clear this. And here we can say all is this, and there's one more number we need to add here, which is 1224444. And now with this we can return all at bisect right. In case you know what this is a binary search. We are running a binary search in all with n as a target. So this will return the first numerically balanced number that's strictly greater than n. Let's run this. And as you can see, this is way more efficient. Here time complexity is log n, where n is the amount of elements in this array. Log n is the time complexity for binary search. So this is it for this problem. If you found this useful, please drop a like, subscribe, and see you in the next one. Bye bye.